All right, so good morning, guys. Where are my students? I'm not hearing anybody. Hi, Alex. Hi, Diallo. Hi, Kay.
Morning, Miss.
Hello, Daniel.
Morning,
Hi,
Miss.
Nivea. Good morning. Here we go. Hi, Cherie. What's Amy? Good. Are you guys seeing the screen?
Miss.
Yeah, we're seeing the screen.
All right, so were you able to download the databases?
Yes, Miss.
All right, good. Wonderful. All right. All right, so we're gonna start. So the lecture notes for today's class is also in that folder. It's supposed to say non-parametric methods and the sign test. So it's also in that folder. Hard copies are here in the classroom as well, whenever you are ready for that. All right. So let's begin. So already we've looked at, what have we looked at? We've looked at assessing and testing for normality. You have looked at data transformation, and I was here waiting for you for the tutorial, but I guess the lectures were so clear. You didn't need me at all. The Wednesday after the Friday that you were told to watch the lecture. So the tutorial? Yes. I told you that I'll make myself available if you have questions. So I suppose the lecture on data transformation was very clear and you guys are fine. And then after that, you looked at probability. For today's class, the non-parametric test that we will examine is gonna build on the foundation that you have covered over the last 2 weeks. Not anything difficult. Once you understood what you're doing over the last 2 weeks, we should be good to go. But before we look at that non-parametric test, we're gonna look at just generally non-parametric methods. So we're gonna talk a little bit about what they are, why is it that we use them, and some of the limitations associated with them. We will also look at a comparison with some of the parametric tests that we've covered. And then the final thing that we hope to cover for today is to look at the first test, the first non-parametric test in the series, the sign test. So we'll look a little bit of the background, and then of course we'll use our SPSS software to generate and to interpret the output associated with that test. So parametric test. In the past, in Biostatistics 1, you would have learned that parameters are statistical properties of a population. And we would have met the mean, mu, the standard deviation, sigma, the variance, sigma squared, proportion, p. And I know that you also know about the corresponding properties of the samples. Those are called statistics. So, you know, for mean, it's x bar, for standard deviation, it's s, for variance, it's s squared, and for proportion, it's pi. All right. No? Okay. Now, many methods in inferential statistics are based upon sampling from a population with some of these specific parameters. And we know that parametric tests often require that certain strict conditions be met. And one of those strict conditions is that the variable of interest should be normally distributed in the population from which our samples are drawn. So we've met that in the past. Now, non-parametric tests, they tend to give the impression, like the term non-parametric, tend to give the impression that our tests or these tests are not based on a parameter, but we'll come back to it later on. So your non-parametric test, these tests, they do not require your populations to have a particular distribution. So your population does not need to have a particular distribution. And when it says that, it really means it doesn't necessarily have to be normally distributed. And because of that, the best term to use to describe these tests would be distribution-free tests. Because when we say non-parametric, it gives the impression that no parameter is involved, which is not entirely true. Because what you will find is that some of these tests, they are based on a parameter, such as the median. So we didn't use the median as much last semester, but you'll find that you'll use it a lot this semester. So the median for the population. So some of these tests are based on comparing medians. But the fact about it is that the term non-parametric has been historically entrenched, and it is currently widely and pervasively used. And so we'll just follow suit and call the tests non-parametric tests. Right? So we'll just work with it. All right. Why are they used? Now, let's say that you've collected your data. Your data does not conform to some of the assumptions that you know are necessary for whatever test that you would have loved to perform. So for example, that concerning normality. If that is the case and you do not wish to transform your data, you can go ahead and apply a non-parametric test, because these tests, they can be widely applied without the strict conditions of parametric tests. You'll also find that you can actually use them with categorical data. For some of them, you can actually use them to analyze like nominal data, which you know is kind of rare when we were looking at different tests last semester. Some persons say they're relatively easier to calculate and they have this intuitive appeal, but I will leave you to be the judge of that. I will leave you to be the judge of that. And then the final thing is that the effects of outliers due to incorrect observations are less than when the equivalent parametric tests are applied. So if outliers are present and you use these tests, your result is not going to be affected, so to speak, by the presence of the outlier, especially if the outlier is actually, let's say you entered a wrong value. So somebody should be weighing like 120 pounds and you put 1,200. So if you have that in your database and you use a non-parametric test, it's highly possible that things will be okay, whether or not that 1,200 is there. All right, so notwithstanding those advantages, there are definitely some limitations of our non-parametric tests. So let's say we have an outlier that is not due to errors. So let's say somebody is actually weighing 1,200 pounds, right? The non-parametric methods, you're gonna find that they're gonna underestimate the effects of those factors. And right here we have like just 4 little ways in which some of those underestimation might occur. So let's say number one, intentional or motivated misreporting. You may actually not pick this up if you analyze your data using a non-parametric method. So for example, if you want to look at, let's say, you're doing a study among high school students and you want to find out how many times they've had sex in the last month. The girls might say 0 and the boys might say 1,000 times. So those are things that we call intentional or motivated misreporting. So they don't really want to tell you what is true. They're going to tell you what they think is desirable. And if you're doing a non-parametric test, you may actually not realize that that is what is actually happening. The next one is inclusion or exclusion criteria. So say, for example, you're looking at nurses. So inclusion criteria is once you are a registered nurse and you're working in secondary care, you're included in the study. When you're looking at, say, for example, a variabilized income, if you're doing a non-parametric test and you just want to, say, look at income of persons at Spanish Town versus nurses in Spanish Town versus KPH, I'm just speaking random. I don't think it should be all that different, but I'm just saying. You may not pick up, if you do a non-parametric test, you may actually not pick up that there is actually some difference in the income of nurses in different categories. So for example, if you include all nurses, so you have your bedside nurses or your nurses that carry out bedside duties, and then you have nurses in like administrative positions, you may not realize that there is an actual difference in the income between those two categories of nurses if you do a non-parametric test, unless you intentionally go and look for it. So if you don't go and look for it and you're just looking generally, you may not see it. Versus if you're doing a parametric test, it might be easier for you to pick up. Faulty distributional assumptions. So for this one, let's say you want to look at something like library use. And you know how it is with library use. The library use goes up closer to exam time. And then after exam, the use falls. If you use a non-parametric test, you may not be able to see that pattern compared to a parametric. And then the final one says outliers as potential focus of inquiry. So sometimes your outliers are not necessarily errors like data entry errors, but they're actually there to prompt you to do some further investigation as to what might actually be going on. And in most cases, when you do your non-parametric test, you may not actually pick up those outliers. So that's why they say non-parametric tests, they tend to underestimate the effects of other factors that might be happening in the data. The second thing is that these non-parametric tests, they are said to waste data. So we're going to talk about this a little bit more, but suffice it to say, in many cases, the actual data points are not used. So the actual data points are reduced. So for example, in the sign test, it's just reduced to a negative and a positive sign. In other cases, the actual data points are ranked, and then only the ranks are used in the analysis. So in many cases, your actual data is not used, and so some persons say that it actually wastes the data. And some people say that the results from some of these tests, they might be very difficult to interpret. I will leave you to be the judge of that. Once you get it, you get it. The main problem is that you have to remember, especially for those that use ranks, you have to remember that you're not talking about the actual data, but the rank of the data. So that's why some people say, okay, it's very difficult to, if you just go and tell somebody about the mean rank of exam grade between male and female is this, they don't know what you're talking about. It's difficult for them to see through it. That's the story. The other thing is that it is said that they are not as efficient as parametric tests, and they usually require a larger sample size or greater differences in order for you to reject the null hypothesis. So that is what he said. So right now we're gonna compare our non-parametric and our parametric tests, and we're gonna talk a little bit about efficiency rating of the two. So if we wanted to analyze paired samples or dependent samples, what is the parametric test that we are going to apply here? The paired t-test. Wonderful. So you can write it in now. Yeah. Oh. All right, so let's write this one into paired t-test. So it's called, this is so fat. How can I reduce the size? No. Okay. Paired t-test, or call it dependent samples, dependent samples. T-test, and this we know can be either Z or T, depending on the sample size. Now the non-parametric analog for the paired t-test is one. So let's see. So there are two non-parametric analogs for the paired t-test. One is the sign test and the other one is the Wilcoxon signed rank test. And what they're saying is, in terms of efficiency, the sign test and the Wilcoxon signed rank test is only 63% as efficient as the paired t-test. And what does that even mean? That means that your ability to pick up a difference, if one exists, if you should use, right. So 63% of the time, you'll be able to pick it up if you use a non-parametric test compared to a parametric test. Some persons say that if your sample size is extremely large, so if it's large enough, you may find that even if, let me not even tell you all the things that are there. So let's say, let me just rephrase. So if your data is normal, what this is basically saying, if your data is normal, you can apply a parametric test or you can apply a non-parametric test. Once the assumptions for the parametric test is met, you can use either one of them. If you do that, you may find that if differences exist, you'll pick it up 63%. You have a 63% chance of picking it up. if you do a non-parametric test. So the story is, if you can do a parametric test, go ahead and do the parametric test. But if your assumptions are not satisfied and you need to do a non-parametric test, then go ahead and do your non-parametric test. In terms of the differences between the sign text and the Wilcoxon sign test, we'll talk about those next week. All right, number 2, 2 independent samples. What's the parametric analysis method for 2 independent samples? Nobody? Independent samples t-test. That's what you're going to say? Okay, independent samples t-test. And again, this one could be Z or T depending on the sample size. Now the non-parametric analog for the independent samples t-test is the Wilcoxon rank sum test. And the Wilcoxon rank sum test is 95% as efficient as the independent samples t-test. Now, if we want to analyze several independent samples, what's the test that we use? So let's say we want to look at age across more than 2 groups, so several independent groups, like age by region, north, south, east, west. No. One way ANOVA. One way ANOVA. Analysis of variance. That's right. And the non-parametric analog to the one-way ANOVA is the Kruskal-Wallis test. So we're going to look at all of these tests. And the Kruskal-Wallis test is 95% as efficient as the one-way ANOVA. Now for correlation, what's the parametric? Parametric Pearson. Right, so the parametric test for correlation is Pearson, and the non-parametric is Spearman. Spearman's rank correlation. All right. Well. Everybody is okay? Can move the slide. All right, let me give you some time. Guys online, are you okay? Are you still here with us?
Yes, miss.
We're here.
Yeah, we're
Yes,
here.
Mr.
All
Good.
right. Thank you. Thank you, guys. All right. All right. So, you're not finished, Jody? Okay. You're not finished? Oh, Lord. It's okay. All right. So you'll recall the hypotheses for determining if there's a difference between 2 dependent samples are as follows. So the hypothesis, the null hypothesis is that mu D is equal to 0. So remember what we did? I think we did something about lead in 1994, 1991, and 1999. So we had lead readings for 2 years, and then we took the difference in the lead readings Remember that? And then the difference became our new data set. And we said the mean of the difference under the null should be 0, right? Because if the readings in 1994 is not different from 1999, let's say under the null, we're expecting them to be the same. So if it's 4, micrograms per liter, then 4 micrograms per liter. So we are expecting everything to be 0. We take the mean of a data set of 0, we're going to get 0. So under the null, that's the thinking. But we know it doesn't work like that. Sometimes we get a difference. And so we want to know if this difference is significantly different from 0, or if it can be considered as something. All right, so that's the null. And then we had 3 alternate hypotheses. That if it's two-tailed, mu d is not equal to 0. Upper tail mu d is greater than 0, and lower tail mu d is less than 0. So that's just for recall. If we were doing a parametric paired samples test. Now we're going to look a little bit on the sign test. The sign test is one of the non-parametric method that is the non-parametric analog for the paired t-test. The sign test can be applied in 3 situations. 3 situations. So yes, it is used for 2 dependent samples, but it can also be applied in other situations. So you can actually use it if you're doing a 1 sample test. You can use it. In that case, you are comparing the median of your sample with a reported median. So you can actually use it in that way. You can actually apply the sign test to categorical data. And your categorical data can be ordinal or nominal. And then the other situation is where you have 2 dependent or paired samples. You can apply the sign test there. Now, what the sign test does is that it focuses on the direction of changes between paired observations rather than their numerical differences. So it doesn't take actual data or the actual differences into consideration. What it does is say, okay, if there's a negative difference, assign a negative sign. If there's positive, assign a positive sign, and then it goes on. So now we're going to talk about the hypotheses associated with each of these situations. So this hypothesis that I have here, says, on the null says, the median. So median is equal to median difference, so median D. So when you're looking at 2 paired samples, match pairs, there's no difference in the median, or the median of the difference is equal to 0. So you do the same thing, you subtract. Let's say if we're supposed to apply to the same lead example, you subtract the 1999 values from the 1994, that becomes your differences, and instead of taking the mean, you want to take the median. And we're saying the median is 0 under the null. And then the alternate hypothesis is that your median is not equal to 0, 2-tailed test. Your median is the median difference. The median difference is greater than 0 for your upper tail test, and the median difference is less than 0 for your lower tail test. For claims involving 1 sample, the hypothesis is going to be a little bit different. The hypothesis is going to be a little bit different. So when you say 1 sample, it means that you're comparing your median with some reported median. You know how we say, oh, the clinic director had this report and the median was this, and then you must compare, so they can actually do it with the median as well. So for this one, so this is just FYI, you don't really need to know it, because what I want to show you is for paired samples, but this is just FYI. So for 1 sample, just so you know, in case you ever need to do it. For one sample, the null is that the median is equal to the reported mean. So your sample median, not sample median, your population from which you draw your data from, that median is equal to M naught. So M naught is your reported median. So there's no difference, it's the same thing. And then the alternate, we still have 3 alternates. So if it's two-tailed, that your median is not equal to the reported median. The next one is that your median for upper tail is greater than the reported median. And the next one is that median is less than the reported median. So that's uppercase M. So the median is often represented as uppercase M, or some books you may see MD. Some books may have that as the symbol for median. Uppercase M or MD. So, for claims involving nominal data, and even, I'm gonna write it for nominal data, but you're gonna actually see that this hypothesis can also be used when you have paired samples as well. So if you have paired samples and your sample size is below 25, so below a certain size for you to be able to apply what did you do last week? The binomial table, this is the hypothesis that we use. But once the sample size gets over that, then the hypothesis tends to change a little bit, and you'll find that you'll be applying the Z table. All right. So the hypothesis for this one is usually based on the probability of success. So this is normally given to you what the probability of success is. If not, it's usually 50-50. So 50% chance that, this happens. So under the null, the probability is equal to 0.5. And then the alternate is that your probability is not equal to 0.5. So this is for two-tailed analysis. I am going to allow you to think about the upper tail, and the lower tailed hypotheses. No, not yet. At the end of the class, we'll come back to it. Let's just do some work, and then you'll think about it while we're doing some work, because it might just be a little tricky. I will allow you to think about it, and then we'll come back to it at the end of the class. All right, so right now we're gonna get straight into it. We're gonna use an example to help us to understand what's going on with the sign test a little bit better. All right, so in this example, we have this drug. We don't know what the name of the drug is, but this drug is hypothesized to lower systolic blood pressure, right? So if it's hypothesized to lower systolic blood pressure, we know already that this is a one-tailed test. Specifically, it's a lower-tailed test. So we have 10 subjects in this example. Subject ID number, first column, subjects 1 to 10. And then we have the baseline reading. So before administering the drug, we took the person's blood pressure, recorded the systolic blood pressure. So that's what SBP means, systolic blood pressure. So the baseline systolic blood pressure, they are here. So for subject 1, that person's systolic baseline systolic blood pressure is 166. Number 2, 135. Number 3, 189. Number 4, 180, and so on. And then we administer the drug and we determine their systolic blood pressure again. So for subject number 1, after the drug, their systolic blood pressure reading was 138. Subject number 2, 120. Subject number 3, 176. Subject number 4, 180. Subject number 5, 160. Number 6, 150, and so on. So we understand that. So that's our data, that's what we have. Now the first step in applying the sign test is that we need to determine the differences. So we're gonna determine the difference between baseline and post-treatment. But it is important for us to define what the difference is and to stick with it, right? So you can change halfway. So it can be baseline minus post-treatment for subjects 1 to 5, and then vice versa for 6 to 10. We have to stick with it. So define it, understand what the results should look like if you define it this way, and then you work with it. So based on your handout, the definition that's there is baseline minus post-treatment. So this should actually say minus post-treatment. I don't know if you have it on there, sir. Please insert it for me. So it should say post-treatment. So that's the definition that we're using. So for example, subject number 1, the baseline is 166 minus post-treatment 138 should give us a difference of 28. Subject number 2, 135 minus 120 gave us a difference of 15. Subject number 4, their baseline was 180, their post-treatment is also 180, and so the difference between those two is 0. Subject number 5, they had a baseline reading of 156. After treatment, their blood pressure went up a bit to 160, and so the difference for them is -4. So we've defined and we've determined our differences. So let's think about it. The hypothesis is that the drug lowers blood pressure. If the drug lowers blood pressure and our difference is defined as baseline minus post-treatment, what do we expect? Do we expect more positive or more negative differences? More positive differences. Wonderful. Good. So keep that in mind. Don't forget it. All right. So the next thing that we're going to do is to look on the sign of the differences. Are these differences positive? Are they negative? Or are they 0? So let's see. 28. That's positive. 15. That's positive. 30. It's positive. Subject number 4, that's 0. Number 5, that's negative. Number 6, -8. Number 7, that's positive. Number 8, positive. Number 9, positive. And number 10, positive. Wonderful. Now, the sign test is based on the binomial distribution. Well, at least depending on the sample size. So for lower sample sizes, your sign test can be based on the binomial distribution. So if we look at it like that, in this case, your blood pressure could either go down or not. So it's either going down or it's not going down. So there are two possibilities. Now, if the drug makes no difference, we expect the post-treatment to be the same as the baseline treatment. So that's it. If it makes no difference, Post-treatment is going to be the same as the baseline treatment. And so if things are happening randomly, we have 10 subjects, so we're going to expect some people's blood pressure to go up, some to go down, and they should be equally. Under the note should be happening equally. So you should have the same amount of ups and the same amount of downs. So 5 positives, 5 negatives, if things are happening randomly. So in that way, there's a 50% chance of being in either category, either your pressure is going up or down. So this is under the no. Wonderful. So let's now determine the number of positive signs and the number of negative signs. All right, so 3 positive, 4 positive, 5 positive, 6 positive, 7 positive. So we have 7 positive signs and 2 negatives and a 0. 7 positive signs. And like you said, positive signs are indicative of a drug effect, the lowering of SBP. So a positive sign here implies difference in the hypothesized direction. So you don't want to forget that. So our sample size is small enough, it was just 10. So we can actually apply the binomial distribution. So for our binomial distribution, in this case,
So you have to make sure that set up the table in a way that the positive side of the table. Let's say you're doing drugs. So let's say you're doing like 3, then you have to set up the table where whichever one you put first.
no worry, it makes it right. So you have to think it through. So even though if you do it the other way around, it's not a problem, but it's best to think it through from the beginning, because when you get to the output and you're writing up, you have to make sure that you're writing about it in the right direction. So it really doesn't matter if you know what you're doing and you can go back to thinking about it. Remember to go back to think about it in the end. Doesn't matter, but it's best to think it through first. It saves you a lot of time. All right, so here we say, so if we're gonna apply the binomial distribution, our n is now 9, and our probability of success is 0.5. Now n is 9 because we ignored the 0 and reduced the sample size by 1. We're gonna come back to talking about zeros in a few minutes. So we'll talk about what to do. What are all the options associated with dealing with the zeros? So we'll talk about it in a bit. But for this example, we've ignored the 0 and reduced the sample size by 1. So this is our question. How likely is it to observe 7 or more successes out of effectively 9 trials when the probability of success is 0.5? So that's kind of what we're asking ourselves. How likely it is to observe 7 or more successes out of effectively 9 trials when the probability of success is 0.5? So now we need to consult our probability tables. So let's do that. Or I guess before we do that, we can do this. So what we're looking for, or maybe not, no, let's not jump the gun. Let's take it one step at a time. Good. Yeah, so let's Is this on the top of the other page? Oh, good. So n is 9. Probability of success is 0.5. So we want to know what's the probability of 7 or more successes. So that means we're going to look at the probability of getting, 7 plus the probability of getting 8 plus the probability of 9 successes. So that's where we got those numbers from. So this is the probability of 7, 0.073, 0.0703, plus the probability of 8, 0.0176, plus the probability of 9, 0.0020. So let's go back. Or maybe we could use it. Good. So from our table, we saw that the probability of 7 successes was 0.0703. And the probability of 8 is 0.0176, the probability of 9, 0.0020. If we take the sum of these values, we essentially end up with this. That's the probability of 7 or more successes out of 9 trials, when the probability of success is 0.5. It's 0.899. Now, what is that 0.899? What does it represent?
The probability of getting 7 or more.
Yes, we know that, but
The probability of the drug actually working.
yes, that's what it represents. But this value actually has a name that you've met before. I don't want to give you any more clue because you'll get it. Anyhow, remember in biostats 1 when we used to draw our curve, and we said the proportion remaining in the tail. What's the proportion remaining in the tail? What's another name for the proportion remaining in the tail after you have compared your computed statistic with that exists in a table? Proportion remaining in the tail is called what? Yes, but what else? What do you know it as? I know you know this. It's okay. All right, it's fine. We figure it out. All right, so you'll remember that we will reject the null hypothesis if P is small. In that, if P is less than 0.05. So you'll remember that. So what's the decision here that we're gonna take? So the probability of 7 or more successes is equal to 0.0899. This figure is greater than 0.05. Therefore, we will not reject the null hypothesis. So what is that value, 0.80899 called? It is the p-value. So it's supposed to come up there. I don't know why I didn't, but it's good for you to think it through. So that's the p-value. So now you've learned how to calculate p-values. Now, so the conclusion is that we do not have statistically significant evidence that the drug lowers blood pressure. So based on the sign test, we do not have enough evidence to say that the drug lowers blood pressure. Oh, that's a long time. Good. All right, so let's go back a little bit to the zero. So we ignore the zero difference value from subject 4. That you'll find is the most popularly used option for dealing with zeros. So in many cases, many softwares, they really just discard the zeros. Some persons say that just throwing out all the zeros is really such a waste and we really don't have to do that. So if you have 1 0, go ahead, throw it out and life should be fine. If you have an even number of zeros, what they say, just randomly assign the zeros to negative or positive. If you have an odd number of zeros, you can drop 1, so delete 1, ignore 1, and then randomly assign the rest to negative or positive. So that's how some people think of it. They don't really like to just throw it out line up, but in many cases, they really just throw them out, reduce the sample size. All right. Now, let me see if I have it on the slide. No, it's not there, so I'll tell you. Now, it may be convenient to look at the probability based on the occurrence of the less frequent sign. So in other words, we could have looked at the probability of getting 3 negative signs or less, rather than its equivalent 7 positive signs or more. We could have done that. We can actually do it at the end, just so not to confuse you. We can do it at the end and I'll show you on the table that you'll get the same answer, but you have to remember in your interpretation what you're doing. All right. So the next thing here on this slide, it says, what would have been the result if we did a two-tailed hypothesis? So if we said the drug either raises or lowers blood pressure, what we would be looking at is the probability of whatever it is, let's say positives or negatives, greater than 7, or negatives in this case less than or equal to 2. So the probability of your positives being greater than or equal to 7 or your negatives being less than or equal to 2 is equal to 2 times, there should be a P here, 2 times the probability of the positives being greater than or equal to 7. So please insert the P right there. So it should be 2 times the probability of X, in this case, X is the positives, greater than or equal to 7. And so if we wanted the 2-tail p-value, we would just multiply our 1-tail p-value here by 2. And when we did that, this is what we got. 0.1798. Let me just double check. Times 0.089. Good. 1798. So 0.1798. Wonderful. Now remember, the analysis of the data is based solely on the sign or the direction of the differences and not the magnitude. Consequently, the sign test has lower power than other competing procedures. So because it didn't even take the magnitude into consideration. So for example, if we look back on the table, a difference, let's take subjects 8 and 9. So subject 8, the difference in blood pressure reading for this person is 16. And for this one, it's 4. So a difference of 16 and a difference of 4 are considered the same way. They're considered on the same level. Even a difference of 28 is still considered as the same as a difference of 4 because you just look at it as a positive sign. So the magnitude of the difference is not considered any at all when you do this sign test approach. So that's just us doing it by hand. Let's use our SPSS software now to generate or to determine if the drug lowers blood pressure. So you're gonna open your SBP data. Most of this is already done for you. So I've already created a database just to save us some time.
Miss,
Yes, go
can I
ahead.
just ask a question, please? From the slide before where you have P open bracket X is greater than 7 or X is less than 2. How you get the X is less than 2? How you determine to use 2?
So I was telling you that I will do it at the end of the class.
Oh,
So
okay.
what I was saying is you can go either way. You can do 7 or more successes. So 7, if you think about it, 7 or more successes is the same as 2 or less successes. But we look at it when at the end, when you're finished.
Oh, okay, okay. All right.
Okay. All right, so most of this is done. The only thing you need to do is right here. We just need to open a database and perform the test. Because I did everything already. So let me close this and all right, so we have our ID number, we have our baseline reading, we have our post-treatment systolic reading, and we have the difference. So the difference is defined the same way, baseline minus post-treatment, and so we're expecting similar interpretation. All right, so let's go. So we go to analyze non-parametric tests, legacy dialogues, 2 related samples. That's quite a bit. So analyze. Do you have the database, Samantha? Yes, it is. All right, just a minute, guys. Just allow it to download.
The Wilcoxon or T-Well?
Tell me what are your options?
Put sign in as well, but should I keep it or not? I just want to touch it.
Ready, Samantha and Jabari? Okay. All right, in the meantime, let me look for the thing for Ready? All right, so we're gonna go analyze non-parametric tests, legacy dialogues, two related samples. Analyze non-parametric tests, legacy dialogues, two related samples. All right, we're gonna click on two related samples. So the difference that we want is baseline minus post-treatment. So I think SPSS does variable 2 minus variable 1. So if we want baseline on the variable 2, then let's transfer post-treatment first and then baseline second. If you did it the other way, you can always use this double-headed arrow to switch them. So we're gonna untick Wilcoxon. Next week we'll do the Wilcoxon, and we're gonna tick off the side. That should be it. We really don't need to do anything else. Unless you want to look at the descriptives, you can generate it, but we don't need to look at anything else. And then we hit OK. Let me just double check that I got what I wanted. So the difference is defined for you here, top left. It says baseline minus post-treatment. So that's what we want. So that way the positives will indicate the lowering of blood pressure for us. So that's what we want. So that we did the right thing. Everybody's okay with setting up the two variables? All right, good. Let me look on this one. Good. So the difference is defined there. That's what we want. And then we're just gonna look at the output a little deeper. Yes, so that's our difference. So it tells you what you're looking at. So we're looking at baseline minus post-treatment. Then we have here, we see here, a superscript A. It says negative differences. So below the table, it tells you what that superscript A means. So it's saying that negative difference occurred where baseline SBP is less than post-treatment SBP, right? So baseline SBP is less than post-treatment SBP. And then B, so there's B here beside positive differences. It says that positive differences occurred where baseline is greater than post-treatment SBP. And then C, so C is right here. So C means that ties occurred here. So basically we have one tie, just one. Good. All right. In the next table, it says exact sig two-tailed. There's also a superscript A. And this is saying to us that what SPSS used was the binomial distribution. So if your sample size was a little larger, it would have said B, and B would mean it used a Z distribution. But in this case, it used the binomial distribution. This value here of 0.180, what is that value? The p-value. Oh, this is on my thing. So the p-value is 0.180. I'm trying to just check something. Don't do anything. What did we get for our two-tail p-value?
1798.
0.1798. Good. And this is what SPSS got. 0.1796888. So more decimal places than us, but practically the same thing. 0.180. If we should do some rounding, we'd get that. 0.180. Wonderful. We are now on par with SPSS. Yeah? What is SPSS? No, but if you want it, what are you gonna? You just divide it by 2, and you should be fine. So Christiano's asking if you want one tail, you can just divide this by 2, and you should be fine. All right, so let's go back to the PowerPoint. So based on this p-value, what's our conclusion gonna be? Are we gonna reject H0 or are we gonna stick with the previous conclusion? So we will not reject H0. So we are not gonna say, what we're gonna say is that we do not have evidence that this drug significantly lowers blood pressure. So if you were writing this up, what you'd say is 10 participants were recruited to determine if a certain drug, so of course, hopefully you would know the name of the drug that you are testing, which I don't know it now. So if a certain drug lowered systolic blood pressure, an exact sign test was used to compare the differences in systolic blood pressure in the 2 trials. Ideal. What is that, Christian? Because it's already on the handout. It's bad that too. Life is easy. Life is easy. No more stressing. Right? It's already there. I put it there for you. An exact sign test was used to compare the differences in systolic blood pressure in the 2 trials. The drug did not elicit a statistically significant lowering in systolic blood pressure. And this is our p-value is equal to, oh Lord. So many decimal points. So P is equal to 0.1180. That's our p-value. That's the evidence that we didn't see any statistical significant lowering of blood pressure. All right. So we're gonna go to the Levine's database. So this is an example we've met before, where we're looking at the number of smoky days before and after a certain intervention. So let's go to Levine and we're gonna carry out a sign test on the Levine's data. Levine. So it's the same procedure. Analyze non-parametric tests, legacy dialogues, 2 related samples. Repeating, analyze non-parametric tests, legacy dialogues, 2 related samples. So we're gonna click on 2 related samples. And what do we want? So the story is that the researchers, they went out, so people were complaining of smoky days. The researchers, they went out, they determined the number of smoky days the people are experiencing, and then they carried out an intervention, and then they went back to determine the number of smoky days. How do we want to define or differences. If the intervention, let me see what we were asked. First of all, what were we asked to do? Oh, so the first thing is, did the intervention make a difference? It says pre minus post. Okay, that's fine. So it's practically two-tailed for the first try. And I think your handout, do we have this thing on the handout? No, we don't. But it's fine. So what they have there is pre minus post. Pre minus post. So if we're doing pre minus post, what do we expect? What's our thinking? So if it's pre minus post, the number of negatives should indicate what? And the number of positives should indicate what?
Like small kids, but it's pre-intervention,
Minus post.
post-intervention.
Positive differences would say what?
You have more small kids.
You have in, and the positive differences would indicate what?
Less
Smoky days, right? So think it through. And then we're gonna untick the Wilcoxon, tick off this side. Pre minus post. So that means that variable 2 should be pre. Variable 1 should be post. So if yours is not like that, then you can just use this. You can use this double-headed arrow and switch them around. And untick the Wilcoxon and make sure you tick off the sign test. And just as I see this, the NEMA, we're not gonna cover it in the course. I'm not even gonna say if we have time, but I know we don't. The NEMA is actually used when you have more than two groups of readings to compare. So let's say you have baseline, and then you wanted to look at blood pressure after 1 week of taking the medication, then 1 month, then 6 months, then you can use the NEMA to help you with that, if you ever need to do that. And it can also be used for categorical data too. So let's say, for example, you want to look at something like if people are satisfied or not with, so let's say the people use telemedicine as well as they use in-person services, right? And you want to see if there is a difference in satisfaction levels for the same group of people. You can also use a NEMA test. So that's just FYI. So let's go. Click OK and generate our output. All right, so let's go. Let's look at this. So our difference is number of smoky days pre-intervention minus post. So we expect the intervention to lower the number of days. So once that's lowered, we expect a lot of positive differences. Anyhow, let's see what's happening. So number of smoky days per year pre-intervention, less than that. So that's A. So the negative difference is 729. So this is saying that for 729 cases, the number of smoky days, what? Post-intervention was greater than pre-intervention. And then B, these are the positive differences, that's 569. So we got what we would have loved in 569 cases. Smoky days being less post-intervention. And then we had 192 ties. So that's table 1. Table 2 now. Table 2. Table 2. So right now, so before we had exact p-value from the binomial table, but this time it's giving us from the z distribution. So what it did, it used the z distribution because the sample size is very large. So the p-value that was obtained, so the z-value is negative 4.413, and the p-value is p is less than 0.001. So this is saying what? The first question said, is this, if it was a two-tailed test, so what's our conclusion gonna be? Is, did the intervention make a difference? So that's the question for the two-tailed test. Is there a difference?
Yes.
Look at the p-values, less than 0.05. So did the intervention make a difference? Yes. Now the question is, what kind of difference did the intervention make? What kind of difference did it make? The number of smoky days increased after the intervention. So if we wanted to look at a one-tailed test, then we're gonna say that number of smoky days, they increased after the intervention. The p-value is 0, so even if you divide it by 2, it's gonna still be 0. It's not a big deal. So yes, there's a difference, but not in the hypothesized direction that we would have loved it. And so that's why it's very important to think through what it is that you love to, or what it is that you're actually assessing, the hypothesis that you're actually assessing. Think through it, think through the data before you start writing up. All right, I think there's one more example for us to do with SPSS, practice exercise number 2, and then I'll show you something else. So this one says, select those persons who have been living within 2 kilometers of the factory for greater than or equal to 85 years. Run the sign test to determine whether there was any difference in the number of smoky days pre-intervention and post-intervention among those persons. So we're going to have to select. So we go data, select cases. So we're still in Levine, so make sure you're in Levine. So data, select cases, and we're gonna click on if condition is satisfied. Then click on,
This data select cases, right?
yes, and then if condition is satisfied, and then you're gonna click on if. Click on if. You're welcome, Musimi. I don't know what you're referring to, but you're welcome.
I was talking about the
Alright.
handout.
Oh, okay, okay. All right, you're welcome. So we are selecting if they lived there for greater than. So years resident within 2 kilometers of chemical factory. So I'm going to click on that, transfer that, and greater than or equal to 85. So years resident within 2 kilometers of the factory, greater than or equal to 85. All right, so we're gonna look at the older adults. What's their experience like? We're gonna hit continue and we're gonna hit OK. Then we're gonna go to data view. Just check our data to make sure that we've done the right thing. Here's resident is right here. So let me look for somebody. 103. So this person has been there for 103 years and they were not crossed out, which is what we want.
Are we there from birth?
Eh? What is it?
Birth?
It seems so. Let me see if there's anybody else that we can, but I think so far so good. 102, 48 crossed out, 50 crossed out, so over 85. I think we can safely say that we did the right thing. 96. I saw somebody was 96, but anyhow, I think we did the right thing. So let's go ahead and run our sign test. So analyze non-parametric tests, legacy dialogues, 2 related samples, and we're should be able to just click OK because everything is already there. The only thing is gonna happen is the sample size is gonna be reduced. Good. So right now, you can see that, I'm trying to zoom in. Zoom in. Wow, I didn't know you could do that. Interesting. I learned something today. I could zoom both tables at the same time. This is cool. All right. So, oh, it's the whole sheet. What? Page 1, page 2. Oh. How did it happen? What did I do? What did I even do? Wow. This is exciting. Anyhow, let's go. So our sample size has been reduced to 10. So in the previous example, we had about 17,000 people or so. So right now, we only had 10 persons who've been living there for more than 85 or more years. So negative differences, 8 negative differences. And remember we said negative differences mean that they're experiencing more smoky days after the intervention. And we only had 2 differences and no ties. 2 positive differences and no ties. And then you realize now that B says we use the binomial distribution because the sample size is small. So now we're seeing the exact p-value. And this time the p-value is 0.109. What do we say about this one? What's the conclusion? It's saying do not reject the null hypothesis. What do you think about that? It is saying that there's no difference. No. The intervention did not make a difference. But what are your thoughts personally? Based on what we saw before with the entire database compared to this now with 8 negative differences compared to 2. What are your thoughts personally?
That the differences were not the desired differences.
Yes, that's true. But in comparison to the p-value.
Okay, so it's to reject hypothesis.
It is saying what?
Do not reject.
Do not reject the null hypothesis.
But then it's still hard to approximately 8% of the days of 8% of the people that live there 85 years old.
before intervention. Right. And so in the back of your mind, you're thinking that something must be going on. But you also know that based on how the scientist runs, it doesn't take into account what the magnitude of the differences are. There are differences that we can see, but the differences might even be very, very marked. But based on how the scientist works, it's not gonna pick that up. For the scientist, you're either having a bad day or a good day. So it's either negative or positive. And that's it. Does it mean that you cannot get a statistical significant result if there's a difference with the scientist? No, doesn't mean that. If once there's a difference, your sample size will have to be extremely large for you to be able to really pick it up. I'm going to give you some homework to do, but I'm not going to give you. I'll tell you next week.
Okay.
Or we'll do it in the class next week. So the take home is really that the scientist is not as efficient as the parametric counterparts. And so if things are okay in terms of your analysis, your assumptions being met, you can go ahead and do your parametric test. All right, there's an alternative method to determining the scientist. Should I show you, should I not show you? I don't want to show you. This is a method for people who have done no statistics at all. All right, so I'm gonna go, it's okay, I can leave the selection on. So it's analyze non-parametric tests, related samples. So instead of going to legacy dialogues, you just go to related samples. So analyze non-parametric tests, related samples, we click on that one. And then the first tab is activated that says objective. We're gonna click on customize analysis. And then we're gonna go on fields and we're gonna place our variables there. So pre-intervention and post-intervention. And then we're gonna go on settings. Settings tab says customize test. We're gonna click on sign test, 2 samples sign test. And then you're gonna click run. I'm moving so fast because I don't really want to show you. So that's what it is. So it gives you the p-value and it also tells you what decision to make. That's why I don't want to show you. Because you already know what decision to make. So this is for the people who don't really know any statistics. They use that route. So it tells you, so guess what? Retain the null hypothesis. So, I mean, if you come in the exam and you're having a little block, you can always try that route to help you, but it's last resort. Huh? I don't know yet, let's see. But it's gonna be after the official June exams.
After June.
Not after June, but
In June.
but after those exams. I just need to check the timetable. Not in May, not in May. Definitely not in May. Like late June, very late June. Yeah. So that is that. Let me see what else is on your handout for today. Okay, so we spoke about that already. These are some references. All right, so if we were supposed to apply the hypothesis testing steps that we used in semester 1. Yes, we're finished with SPSS for now, for today. You can shut down. Says, so we'd go, set up our hypotheses, the drug makes no difference, the drug lowers blood pressure. So you can put it in words or put it in symbols, which we still need to talk about the symbols. We could do it right here. So before we said Let's discuss that, right? You can discuss it right here. So we said under the null, probability of success is equal to 0.5. And then the two-tail is that P is not equal to 0.5. So this is two-tailed. So what is upper tail and what is lower tail? Hmm? 0.25 is not equal to 0.25. Expand on it and tell me what. Is less than 0.05 for upper tail. All right. And then what? P is lower than 0.05? Oh, I already have P. P is greater than 0.05. All right. If there are no other responses, I will allow you to do it for homework. And we'll talk about it next week. But it's the vibe.
I was saying that he was,
P was greater than greater than what?
0.05. Point
0.25. So what do you get 0.25? P is greater than 0.25.
the lower.
All right, walk us through the thinking.
Half the probability.
But why would you do that? Because it's one tail. Could it be what, Christian?
No, I'm sorry.
Why would you do that, Jabari? You're not necessarily wrong, you know. I just want to.
All right, so the probability of getting one will come up. 50%. And the probability of only getting a partial of the outcome would not be the same. It would have to be half. That's what I was saying. So the P is greater than 0.5, half of.
Which you're not wrong in terms of how you're thinking about it. You're not wrong. But there's another convention that we could use, which probably might be a little bit more intuitive. We could say the probability of the positives. So, let me see. So P positive differences. So for upper tail, and then this is also, you have to remember how you define whatever you're doing. So P positive greater than the probability of the negatives for your upper tail. And as I said, this is not set in stone. It's actually based on your definition of your difference. So you have to be careful. And then for the lower tail, P positive is less than P negative. But in terms of our example and how we defined our things, our lower tail would mean that what? We need more positive than negatives in order to say that the drug lowered. So for our example, this one would have been our lower tail. So I just put it like that because sometimes that's how the books they have it, but you also have to remember about your definition. But this is also FYI, don't need to stress about it. You don't need to come in the exam and talk about it. Nobody will really ask you about it. Really, it's FYI. FYI. All right. If you want to talk about it, we'll entertain you. That's all. But we're not gonna ask you. We might ask you what the hypothesis is, like generally speaking, but nobody's gonna go down into these things. What are you saying, Samantha? Maybe. If you talk about it correctly. If we talk about it correctly. Yes, usually. All right, so regular step one, so to prove hypothesis, select our alpha level, 0.05, we select our appropriate statistics. So usually the test statistic for the sign test is the smaller of the number of positive or negative signs. So it was Kay who had asked us about how do we know to use the probability of the two. So in our example, we got just I don't want to move the slide, so just keep back on your handout. We got 7 positives and 2 negatives in our example. So, or maybe I could just do it right here. So okay. The probability, you remember this table that we generated last week? That it's almost normal. So this is what it is. So the probability of getting 7 or more successes, in our case, it was 7, 8, or 9 because our sample size was 9, is equal to the probability of 2 or less successes, or those would have been like failures. It would have been considered failures, but it's failures, 2 or less failures. That's only if the probability of success is 50%. So it only works if the probability of success is 50%. Right, it's good that you said that. So it only works if the probability of success is 50%. So if we should do this, so 2, 1, 0. So let's look at the probability of 2. So at 0.5, so we're gonna see it's 0.0703 for 2. Probability of 1 is 0.0176. The probability of 0 is 0.0020. So okay, go ahead and take the sum of these for me and tell me what you get. 0.0899, which is what we got when we did 7 or more. You remember that?
Okay.
Good. So right, so that's why it doesn't matter which direction you go, but it's best to work with the direction that's more intuitive to you. So when you're writing up, you don't get confused. But if you are doing it this long way, what they say is that it's best to use the smaller, if you're gonna use the sign table, the smaller of the 2 is what is gonna be your test statistic. So in this case, it would have been the 2 negatives. So the appropriate critical value for the sign test can be found in the table of critical values for the sign test. So to determine the appropriate critical value, we need the sample size or the number of matched pairs. So for us, it's 9. And our lower tail level of significance is alpha equals 0.05. So this is the table. So the sample size is 9. And 1 tail level of significance for 1 tail at 0.05. So the critical value here is 1. Excuse me. Critical value is 1. So what we're gonna do, critical value is 1. So the decision rule is as follows. Reject H0 if the smaller of the number of positive or negative signs is less than 1. So because our critical value is 1, That's why we have 1 here. So the smaller of our negative and positive sign is what? It's 2. So 2 is not less than 1. So that means that we are not good. So it's all there. So we compute the differences, we ignore the ties, we do that, we do that. So we have 2 negative, 7 positive. So T, the calculated test statistic is gonna be 2. So we will not reject H0 because 2 is actually greater than 1. We do not have statistically significant evidence that the drug lowers blood pressure. So that's basically it. So that's the sign test in a wrap. If there are no questions, next week we're gonna do the Wilcoxon sign rank test. If there are no questions, that's it for today. You have 10 extra minutes. I think that we should start the next topic. I'm joking. All right, guys. Guys online, any other questions? Anything else that we need to clear up for you? Otherwise, this is the sign test. You can always come in and talk about the sign test and run your things, and we give you a database to do the sign test. It's a topic that you can actually choose to talk about, which is not a long topic.
Miss,
And
Miss,
you can, yes.
yeah, I'm
Yes,
saying
yes,
that
Kim.
I'm gonna have to come into you and sit down with you to go through some of these. So there's a few things that still not clear on what I need to come in physically and speak
All right.
with you. Yeah.
Okay, no
So
problem.
to be clear,
Mhm.
the sign test is what we started today.
No, last week we did binomial probabilities. So that was really just to set the foundation for this one. So if you want to come and talk about probabilities, fine, but
But I wasn't here last week. The video uploaded,
yeah.
and I didn't get the video for the internet uploaded to the site, or is it that?
The one that I sent in your email?
I didn't send something down.
The one that when you call me on the phone and I said, give me your email address? No. All right, I'll send it after this. All right, guys, have a good weekend. Take care.
Bye, man.
Bye-bye, guys. Bye-bye. Oh, boy.
But it's fresh.
Beef.